get knowledge from all parts of the world, even though we are physically very much separated. So this webinar is also aims to connect people who are at different parts of the world with with the students of our college, and maybe to some other colleges also if interested. For the time being, we have not connected to other colleges, so people all over the world can watch these such webinars, and they can exchange knowledge. So that is an opportunity that has been brought by the COVID-19, even though it is a very difficult situation in all other aspects. And that is one good aspect as far as the COVID-19 pandemic situation is concerned. Now, coming to the today's program, we are going to hear from one of my students, as I already said, Dr. Abdullah Abdulsalam, who was in Sir Syed College as a BSc student in the year 2006, I think, and thereafter he left for MSc at Aligarh University, and from there where he completed MSc, and thereafter PhD. He started doing PhD there and completed PhD from BARC, and he took PhD in nuclear science, which is one of the major areas of research as far as physics is concerned. And his subject is particle physics. Again, it is a a lot of advancements are taking place in this field. And thereafter he moved abroad, and he's associated with the famous CERN, that is the European Council for Nuclear Research. It is he's also he has done research work in connection with the LHC, Large Hadron Collider. And thereafter he came back, and now at present he is working in Saudi Arabia. He's assistant of Jeddah University, and you can the students especially can get a lot of motivation from him, because he belongs to Parayangadi, and he's the son of managing director of our college, and SAP Abdulsalam Sahib, and he has come from background which is quite similar to you, and he had right from the beginning he had an eagerness in physics, and he developed it, and he has grown into a good research scholar and a good academic personality. And I take this opportunity to invite him to this webinar. Then we have with us our beloved principal, who has taken initiative in starting such a webinar. And on the just for a formality, I am inviting him to chair this function.
Thank you, sir.
Iqbal sir, please.
Thank you, sir.
You are welcome. Then we have with us, I think, SAP Abdulsalam. I think if he's there, his name is there. SAP Abdulsalam, Managing Director, Wadi Huda. I welcome I also welcome him on just for a formality, because he is part of he's the backbone of this institution, and his contribution to this institution is enormous. And formally, just for a formality, I invite him to this webinar. Also, Mr. Muhammad Sajjad PK, Academic Director. I welcome him also, Academic Director of Wadi Huda. Just for a formality, I am just welcoming him to this webinar. And then we have Secretary Mr. Farooq Usman, Tasliq Islam Trust, and I invite him to this webinar. Then I invite the teachers of this department, Jasira and Safina. We are again, it's only a formal thing. I'm formally inviting them, and all the students are welcome. And I think you are all eager to hear from Dr. Abdullah Abdulsalam, and we can expect a lot of motivational things as far as his talk is concerned. You can get a lot of knowledge as well as motivation from him. And with these words, inviting all the others, who are watching this webinar, with these words, I invite our beloved principal to chair the function.
Excuse
Principal
me,
sir,
sir.
please.
Could
Okay.
you please mute others? A lot of distraction, that's right.
Others, please mute their. Okay. So I invite our beloved principal to chair the function and address the gathering. Okay.
Mr. Kiran means you can unmute all others. Sorry, you can mute all. Okay. So, thank you, Ramendran sir, for your kind words. And we are very happy and we are really motivated. That means Dr. Abdullah Abdulsalam. And he is the son of our managing director. And he's a native of Bayangadi. And he's just like you people, means just like you people. The people in the Saranya, please, can you please mute your audio?
The host can mute all other people. The host can mute all other people.
Yeah. So we are very happy that means we got an eminent personality, and that personality is from the native of Wadi Huda also, and from the son of SAP Salam Abdulsalam sir, and he is our managing director, and we are very much proud about him because he's a as our Ramendran sir said, means it's a very wonderful moment for our physics department. And even though means we were trying for the last so many years to interact with the students, but unfortunately means we were unable to get him. But the corona or COVID makes us a lot of fortunate because we can contact a lot of people around the world. And this meeting and this Zoom meeting and this Zoom webinar, I think a lot of people are watching this one. Even means through Zoom. Zoom is only limited for our internal purpose, means internal teachers and students can watch this program. And the remaining students, the out of means other students of other departments and other colleges, and even from national, international, they can watch the videos from our Facebook. Means it is available in our Facebook Live also. So I hope that the things are going very well, and we are eagerly waiting for his speech. And I don't want to introduce him again because already means our Ramendran sir introduced very well about the things and all. So I hope that means his journey for physics, his journey through physics will inspire us, all of us. Because I am also very happy because I am also a part of physics. Means actually my post graduation is in electronics. It is also from physics. So, and it is the beginning of our webinar series because we are planning webinars in different department and physics, psychology, commerce, and so many departments are there. So I think this is the first webinar in our webinar in this academic year. So it will be a motivation for other departments and for a competition also. So I wish all the very best for this webinar, and I invite Dr. Abdullah Abdulsalam directly to enter to the webinar. So, sir, please. Kiran, please unmute.
Okay, now I will share my slides. Okay. I think you can see my slides, right?
Yes, we can see.
Oh, okay, fine. So, respected principal, Iqbal sir. Sorry, someone is speaking. Sorry. Okay. Respected principal, Iqbal sir, and the respected professor, my professor, Ramachandran sir, and all other dignitaries and my dear students. A warm good afternoon for all of you. And thank you for inviting me and giving such an opportunity to present my knowledge and my understanding and my work. So first of all, I would like to thank you, my professor Ramachandran sir. He was my tutor, he was my mentor in Science College. And from my heart, I would say that I got many motivation and many sincere lessons from him during the class and out of class. So today's topic is curiosity for the fundamental constituents of matter. So this is like a quest. This is like a search for the fundamental blocks of the universe. So let us see what is our universe when it is started. So we have a very well-defined theory, Big Bang theory, that is well-defined in the sense that it is whatever it is predicted, whatever it is suggested is according to this theory, it is happening in the course of time. So our Big Bang, when the Big Bang started around 10 to the power 40, 10 to the power minus 44 years back. So from that, it is evolved in a different stages of the particle evolution. So in the beginning, it was very hot and dense matter, very hot and dense matter. At that time, we are calling that this is core gluon plasma. After the Big Bang explosion, then you can see that while it is time increasing, you can see there is a three scales: time, temperature, and energy. As time increasing, the new evolution, the new the stages of the new evolution, you can see in this picture. So in the first stage, there are elementary particles like quarks, gluons, and some subatomic particle like W and Z boson, and some top quark. Then after the interactions, after the interaction of these particles, after some time, during this time, the particle is with a strong, we will see what kind of interaction we will explain later. But due to some interaction, it forms some bound states. So that is around this 10 to the power 2 seconds after the just Big Bang. Then again, it is now the bound state. There are some neutral particles. There are some charged particles. There are some stable particles. There are some unstable particles. So during this course of time, now new particles emerge like electrons, positons, neutrons from these elementary particles, from these elementary quarks and gluons and other subatomic particles. So you can see that after some years, like 10 to the power 5, that's around billion years. Now the new interaction coming to play, that is electromagnetic interaction. So at that stage, the atoms, molecules coming to the picture, they are start to interact. That will slowly, gradually coming to the new state of new state of matter. Also new form of the building blocks. So next stage, you can see that stars, galaxies, and other kind of the matter in the universe are formed. Now finally, we, the human being, evolved in this stage. around some billion years after the Big Bang. So this is some initial kind of some evolution of the particle and the development of the particle physics, or not the particle physics, the studies of the different interaction and the creation of the particles it shows from this picture. Okay, now the basic question is, what is the fundamental of the every object in the universe? This is not a new question. This question is very old. We can say that since from the start of the creation of the human being, or the evolution of the human being. So people start to ask from the long back, what is the world made of, and how it is, what is the force that holding together. So these were the questions that that was arisen in every era of the time. So during by the observation, by the testing, we can say, in the earlier time only the observation, we can say. So people understand that, and people start to think that why the so many things in the world share same characteristic, like the mat or the stuff, the things in the world have similar structure, or the stuffs in the world have similar kind of atoms, or the stuffs in the world have similar chemical properties. And from the observation, people have to come realize that the matter of the world is made from some few fundamental building blocks of nature, few elementary building blocks of nature. What I mean fundamental, what I mean elementary means it is like point-like particles. It is some basic building blocks of matter. That means there is no smaller particle inside that the parent particle. That's what I mean fundamental. There is no smaller particle inside it. There is no other particle. There is no structure in. It has no structure. So that's what I mean the fundamental or elementary particle of physics. So in the earlier time, people were thinking that the building blocks of matter I means whatever we are watching, we are observing in the universe, that is we are calling matter, like water, any ice, any mountain and fire, etc. Anything in the world what we are watching, that is we are calling in the large category as a matter. So the earlier people, it was they considered that the building blocks or elementary or the fundamental things inside each object is like fire, water and earth, air and earth. And in the ancient time, the Greek thinkers, they were the first time they classified the fundamental elements as a fire, air, earth and water. And in India also, we have a very rich philosophy, we have a very rich history in the knowledge. In the Sankhya Karika by Ishwara Krishna in the 3rd century AD, maybe in some BC. In that text also, it claims that there are some 5 elements of the basic fundamental blocks. Like it says that space, air, fire, water, and earth. But these were merely some observation. Merely, it's not like some sophisticated experiment. It's not like some from these claims, these arguments, not from the sophisticated testing. So later, after some like century later, so people developed many technology, people developed a new experiment setup. So based on the experiment setup in the early 1800s, John Dalton, the famous scientist who introduced the atomic theory, he introduced that according to the atomic theory, he proposed that all matter was composed of the atoms. It means he proposing atom is the fundamental particle. Atom is the basic building blocks of every object in the universe. So according to his theory, it is indivisible. That is why the atom name itself means, and it is indestructible. We can't destruct this particle. That means it is like from the beginning. It is like this. We can't divide. We can't destruct. So this is the building blocks of matter. So according to this theory, every phenomena, every physics, every science phenomena can be explained more or less well. But later experiment means with more advanced technology at that time suggested that no, atom can't be the fundamental. There are some experimental evidence. It shows that it shouldn't be the fundamental, and there should be some other small particle inside the atom. We will come to that things. So around 1900, people thought of atom is some there are many models, as you know, as you studied during your first year or second, during your higher secondary school or in the first years of degree class. So the atom has, they have many, they were suggesting that the scientists were suggesting or proposing new models to explain well the characteristic, the properties, whatever we have observed in the experiment. They are developing new theories. So one of the theory that's plum pudding model for explaining the atoms at that time. So, but it was not accepted well because of it is not explained well whatever the observation from the experiment. And so the still question is atom is fundamental, because why this? The question is that according to this John Dalton, he was suggesting a good theory and based on the atoms, and he is suggesting that it is indivisible, and this theory could explain many observations, many phenomena in the science, in the chemistry and physics. But later experiment, it shows that it is something contradicting his arguments, his claims. Okay, so now we have later the people realize that atom can't be the fundamental. Why? Because they could categorize the atom into different groups which has similar chemical properties. It means that we can arrange the atoms in different groups. It has a similar properties that is based on something inside the particle, each atom. So it means that the atoms were made up of something simpler or smaller building blocks. This was the one indication that atom could not be the fundamental or elementary. Later, as everyone knows, that's a very well powerful experimental proof from the gold foil experiment from the Ernest Rutherford. So from this experiment, the bombardment of the alpha particle in the gold foil nucleus, we understood that this positive alpha particle is substantially deflected, is substantially scattered back. So it means that there must be something inside the atom that could deflect the alpha particle, and that should be some small, dense, and positive charge particle. So later we understood that this is the core of the atom, and we call the nucleus of the atom. So now we understood that, okay, atom is not the fundamental. Atom is not the elementary. It is something inside. It has something inside it. It has some structure. So what are the new things then? So let us see. So are the protons and neutrons elementary? So during that time, as we know, many experiments were performed in different labs around the world to understand what is the nature of each atoms, to understand what is the fundamental things, to understand what is the basic things in each atoms. So some people suggested that this is the hydrogen nucleus that is same in each atom? Some people suggest that no, it is some other particles that is common in every atom. So one of the scientists brought out hypothesis. His suggestion was hydrogen was the building blocks of the all elements. So this suggestion was from his according to his experiment, and the discovery later understood that the hydrogen nucleus is present in all other nuclei. As you know, hydrogen nucleus is basically one proton. At that time, proton was not discovered. And this discovery, the understanding of the hydrogen nuclei as a one particle state, like a proton we say, like one particle state, that led to hydrogen nucleus as a proton. Proton means itself is a first. It's a first in the periodic table. And this proton and the neutron, that's the components of the nucleus, is later discovered in 1919 and 1932 in the other experiment. So what I'm saying that, see, the people were doing experiment. According to the experiment, people are suggesting new hypotheses. People are developing new theory, so that one could explain what they observed in the experiment. So one of the thing is that proud hypothesis was hydrogen was the building blocks of the all elements. That is according to the experiment that only hydrogen basically means that one particle nuclei that is common every atom. That was his observation in his experiment, from this experiment. So it is like that. From the theory and experiment, it's like each and take and give and take a relation. So once the theory proposed according to the experiment will conduct some new setup. Then from the observation, then the theory and the model will try to explain. If the theory or if the model can't explain whatever the data or what we observed from the experiment, then the theory should be modified, or the hypothesis should be modified to explain the experimental observation. Okay, so during that time, meantime, many other experiments in the different world was held at various labs with the discovery of new other particles like electrons, neutrinos, muons, and so many other things like subatomic particles like pions and kaons. So what I am saying that all these are like the curiosity or the search of the new other particles, new elemental particles. All this was happened in the search of new fundamental constants of matter. So one of the example is that, see, in the beta decay, the conservation in the beta decay, at that time the neutrino was not discovered, and the neutron beta decay, you know, the neutron decays to the proton, electron, and the antineutrino. And at that time, neutrino was not discovered. But while people are calculating the energy conservation, momentum conservation, and this one, angular momentum, but in the beta decay, angular momentum is not conserved according to the experiment. Neutron decays with some energy, and the final particles like protons and electron it has some energy in the detector. But according to the experiment, it is not conserved. So what happens? So later, the Dirac proposed that there should be some missing particle that is invisible, that is neutral. That's why neutrino, the name itself shows. He suggested there should be some particle, invisible particle. Later in the experiment, we understood that there is a new elementary. Elementary means there is no particles discovered so far inside the neutrino like the electron. It was discovered according to this proposal. Also, the discovery of the positron later in the stage suggested that there could be antiparticles for each particle. There should be antimatter for every matter in the universe. So it's like pairs, every particle in the universe, it's like created in a pairs. So, as I said, in different labs, there are huge variety of activities were performed, experimental actions were performed to find that, to understand the nature, to understand some fundamental, to understand the properties of the fundamental particles. So in that, during that stage, like from in the early 19th century up to the 1950, 60, there are huge number of additional particle. Additional particle, what I mean, other than the protons and neutrons, like pions, kaons, sigma, and all other unstable, all other the subatomic particle, many other subatomic particles were discovered during this time. Now, like the periodic table of the chemical elements, the people start to classify, categorize the subatomic particle like hadrons. So as I shown here, the particles, like we can categorize leptons and hadrons. Lepton basically electrons, muons, and neutrino. And at that time only hadrons. At the 1950, 60 only hadrons was named, because there was no the quarks and gluons. Quarks and gluons were not discovered at that stage. So from this observation, like one of the sophisticated, we have to say, one of the sophisticated classification, categorization from famous scientist Gell-Mann, based on some theory. That's a group theory, we say. This is a mathematical theory, but it is very, very powerful and a very high level application, and so many applications in the physics also, in chemistry also. According to based on the group theory, they categorized the particles in this form according to their charge, according to their quantum number. Like we can say quantum number, spin, charge, orbital quantum number, and like other quantum number, like we have the strangeness quantum number. At that time, this is some new quantum number for the particle physics. So this classification named as eightfold way, in the sense that, okay, we can categorize the particles neutron, proton, sigma, all these according to their strange quantum number. Means, I will explain what is strange quantum number later. And according to their spin, according to their charge. See, when the scientists developing this classification, this categorization, this sigma 0 was not discovered. When the scientists suggesting this decuplet, this omega minus was not discovered. But according to them, then the lambda, sigma, cascade, there are one more particle was not discovered at that time. But they suggested that, okay, the particle can be categorized according to some symmetry, according to some basic laws. So they can categorize like similar properties of the quantum number or similar charges. So they arranged all the particle, but this particle was missing at that time. This particle was not discovered. Using this classification, using this characterization, using this this arrangement of the particle in a very beautiful symmetry, they propose that there should be a particle here, and the charge should be minus, and the strangeness quantum number should be -3, and in the later stage we understand that the omega minus discovered in the experiment. So what I'm saying that, okay, people like in the periodic table, in the for the chemical elements, for the atoms, we can arrange, we can categorize, we can classify particles in a very unique way. Unique way in the sense what I'm saying that this is based on some group theory. So this is some pure mathematical group theory that we apply here. So that gives to new thinking that, okay, there should be some new particles. There should be some other particles. That led to the discovery of the omega minus. This is and also one thing I want to say that every particles, see how beauty is. So every particle is, we can arrange in some hexagon or decuplet, octet. This is some very beautifully we can arrange, like in the chemical elements in the periodic table, we can arrange the particles in a specific in a specific shape. Okay, so from this people understand that, okay, there should be, if you can arrange the particles like this, it is not, there should be some difference between this. If they are same, there should be some difference that can be separate, that can separate the particle like this in this structure, in this format. So the Murray-Gell-Mann and in 1961, and the Murray-Gell-Mann is a famous scientist. He was proposing the idea of the quarks, and the Newman introduced the classification of the Quark model. In this Quark model, they were suggesting that hadrons means protons, neutrons, like pions, kaons, all other particles. That shouldn't be fundamental. That shouldn't be elementary particle, but instead it should be some composite of the other smaller particle. At that time, they suppose that they are giving some name quarks and anti-quarks also, anti-quarks. And this is some according to their theory only. But later in the experiment, in 1968, deep inelastic scattering experiment, DIS experiment, deep inelastic scattering experiment at SLAC at the US, showed that proton contained much smaller and point-like object, not an elementary particle. But it means so far until this year, the scientists or the people who are believing that proton can be an elementary. It can be the building blocks of all the objects in the universe, but the experiment showed that in different way. So people start to think in a different way also. That is the way. That's why they proposed Quark model, and it was successful in that level, in that way. So why Quark? Why the smaller particle inside the neutrons or any hadrons? Before coming to this, I will show you one more thing. Okay, I will first see this slide. So testing theory. We have a theory, we have a model, we have a hypothesis. Like I just talked about the Quark model and the hypothesis. That's the Gell-Mann and the Newman. These two great scientists were proposing that there should be some smaller particle inside the protons and inside the hadrons, any hadrons. But why they are suggesting? Is it how will I say, trustful? How we can take that arguments, their proposal? So we have to do some test. So to test theory. Physicist has to do some experiment using the knowledge what they have to find out what they don't know. So in our particle physics, particle accelerators, we will come to that, how they are working, is a powerful tool to study the structure of a particle. It's like that. Two particles colliding each other, and they are interacting, the particles inside each particles. And the idea is, principle is, the accelerators can resolve, or that can enter very small structure or resolve the very small structure by colliding the particle with a high momentum and short wavelength. So according to de Broglie principle that you know, So the wavelength of the each particles or incoming particle or any object can be reduced by the, or it is inversely proportional to the momentum of that particles. This is Planck's constant. It means that the size of an object is inversely proportional to the momentum or energy of that particles. So using the principle, let us see. Okay. We know the alpha nucleus scattering, like a gold foil experiment by the Rutherford. So in that experiment, you see that, okay, alpha nucleus scattering. So the alpha energy is around 10 MeV, that's a 10 mega electron volt. So at the if it is that the incoming alpha particle energy like this, the wavelength will be around 5 Fermi meter, FM. So Fermi, then it means that alpha particle has this much the wavelength. So usually the nucleus is 1 Fermi, right? So it means that alpha particle can't resolve the inside structure. It can't go inside. It can't look inside what is inside the nucleus because alpha particle size is 5 Fermi and the nucleus is 1 Fermi. So one has to reduce the wavelength or the size of the alpha particle or the incoming particle so that it can go inside the target, like here the nucleus, so that it can go, it can search, it can understand, it can the particle interact inside the particle. So let us come to this stage, like electron nucleus scattering. So in that case, here the alpha is incoming, here the electron is incoming, and scattering with the nucleus. And okay, one thing I want to say that, okay, because it can go inside the nucleus, it can't look inside the nucleus. There it will interact only considering that nucleus is a point particle. So that's why Rutherford discovered that there should be some dense center inside each atom, but he could not at that during the using that experiment. One cannot say, okay, nucleus consists of some protons or other particles because the wavelength was high. It can go in, it can resolve the nucleus or it can go inside the nucleus. So while let us this one, okay. Okay, here the example. Electron nucleus scattering. So 100 mega electron volt means the incoming electron has 100 mega electron volts. According to this, the wavelength of the electron is 12 Fermi. So it can go inside this. It can still interacting with the nucleus as a point. But when we increase like 1 giga electron volt, see the wavelength is like 1.2 Fermi. It means it is more or less comparable with the size of the proton, the wavelength of the proton. Then it can go inside the proton. It can interact the inside particles of the proton. So that's why the cross section drops in this case. See, if it is the point particle interaction, if it is means if the nucleus is point particle, the graph should be like this. But see, there is a angle is something larger. It means that the target here, the nucleus, here the target is proton, is something structured, something inside it. That is why there is a large angle scattering is happening in this case. So now we understand that, okay, there should be something inside the proton. It is not the proton it is not the proton that is elementary or the fundamental, something there is inside it. So proton is structured. So yes, this is the case from, this is the evidence from the experiment. At the same time that Gell-Mann and Yuval Noah was proposing some Quark model, suggesting that, okay, these protons and hadrons should be composed of some smaller particles. Yes. So now we want to test the theory. How we are testing the theory? As I told you, the particle accelerators are powerful tool to study the power of the structure of the particles. So as I said, this is like a more explanation. See, suppose we want to study about the quark or quark structure. If the electron wavelength, if the size of the electron is this much, it can't explore the structure of the quark. It can't go inside quark. So the electron wavelength or the size of the electron should be very, very small or comparable with the size of the quark. That's the idea in the accelerator. So we know that all the particles have wave properties. So physics can use particles as their props, means in this case, the prop means electron can use to understand the structure of the proton. Now the electron can be used to understand the structure of the quarks. So if you increase the energy, we can reduce the size of the incoming particle. We can reduce the size of we can reduce the wavelength of the incoming particle so that it can enter the target. It can search inside target. That is the idea that's the principle used in the particle accelerator. So this is some graph that shows that how the momentum increased according then how the wavelength is decreasing. Okay, so from the experiment, we understood that there is in a different experiment from the astronomy, astrophysics, and chemistry, physics, we understand that we have a different object with a different size from different in that scale, like a galaxy, starting from the galaxy, then that is mainly mainly tested with some telescope in different places of the world, and we have the Milky Way, other solar system. Then we have the animal. This much says that we just observe using that our eye. Then cell we can use microscope. Then electron microscope. Using the electron microscope, we can understand. We can study about the atoms or the similar object in that size. And beyond the nucleus, we have to have something new techniques. That's where we are using the accelerator. Accelerator means basically it is accelerating the momentum. Basically, the accelerating momentum means it can reduce the size of the incoming particle. Here, the incoming particle, suppose electron, we can reduce the incoming the wavelength of this. Then it can go inside this quark so that we can understand the structure of the quarks. Yes. So from the experiment, we understood that there are two types of point-like constituents. One is the one we can say leptons and quarks. And in the leptons, we have the electron, muon, and tau. And the neutrinos, the electron neutrino and muon neutrino and the tau neutrino. And in the quark, we have the up quark, down quark, and the strains, top and bottom. So, as I told here, people were suggesting that there should be something inside the Quark model. And from the experiment, it is also shown that there should be some smaller particle inside each hadron or each neutrons and protons. And later experiment, it is the confirmation that a smaller particle that we are calling the quarks. And later we understood that there is another particle that gluons. We will come to that stage. And there is some force carrier. What is force carrier? So we will come to force carrier later. Yes, matter and antimatter. As we saw here, as we have seen here that we have the electrons, muons, and tau. Similarly, we have the quarks. So every matter means that particle will be using that particle, every object in the universe is built. So that is why we are calling matter. So every type of matter particles we have found, there also exists a corresponding antimatter particle. So we have up quarks. So similarly we have anti-up quark. So similarly we have top quarks. So in that case we have an anti-top. So every particle in this case, we have a particle and antiparticle, or a matter and antimatter. So this is we have the so many experimental evidence for the matter or antimatter, or for the particle and antiparticle. So this is one of the old photo that's from the bubble chamber experiment. So mainly to separate the particles and antiparticles, or the magnetic field is used to separate these particles. So the magnetic field in this chamber, yes, please.
Yeah, ask one doubt.
Yeah, please.
What is that USCD under the picture of Quark? The last slide.
Which line? This one?
Yeah, this one.
Sorry?
UDCH. What is that UDCH?
Okay. Okay, sure. Okay, what I am saying that so far we have, I will explain some category here. Yes, we have a particle categories here. That's how we can categorize in a different broad way. Like in the largely we can leptons and hadrons. So leptons basically the electrons, that's an electron, muon, and neutrino. And hadrons, at that time only hadrons was in the, like we say everything is like the hadron, not separately mesons and baryons. But later we discovered that there is some quarks structure inside hadrons. Then we separate the hadrons into mesons and baryons. Meson basically bond state of two quarks. Baryons basically the bond state of 3 quarks. So how many flavors of quarks? That's what it says. There are 6 kinds of quarks, 6 flavors of quarks. That is up. This is the some name. It is the scientist given. Up quark, U, and down quark. And it has some different properties, like the charge is and different from this one. Then the charm quarks and the strange quark. This is the top quarks and the bottom one. So these are the 6 flavors of the quarks. Flavors means 6 kinds of the quarks. So here the charge is different from each charge is different from others, and mostly all the quarks have fractional charges. That's the fractional charge means not unit charges. Fractional charge is the up quark charge is 2/3. Down quark is minus 2/3. Then the charm quark also. Then strange also this is minus 1/3, etc. So all the quarks have different fractional charges, and the quantum also. Oh, I think this is the question, right?
Yes, sir. Thank you.
Okay. Now let us see. Okay, we were in the slides. So using the magnetic field, we can separate the particles and antiparticles. So clearly we can see that. So this is see how the things when the particle, like 2 protons collide at very high energy. So as I said, if it is a proton is very high energy interaction scattering, it can go inside the proton. It can interact inside the proton. Then it means that now the interaction is between the quarks in each proton. Okay. So from that, this new particle is produced. New particle means new mesons, new hadrons, new baryon is produced. So how will you detect? How will you understand that particles? So one of the method earlier, it was using that bubble chamber. So this is some new some specific liquid was used. and while the colliding, while the particle production, they will take the picture using this photo the illumination, so that we can see that the particle is going and antiparticle is in different way. So one of the example is that different the electron and positron pair is produced, and it is deflected in the magnetic field in this side, and the anti-electron, that's a positron, is deflected in this side. So similarly, we can see many other particles, many other the matter and antimatter, or particle and antiparticle. So in this, what I mean that we have the basic fundamental, the basic concept of particle like leptons and quarks, and we have a force carriers that I will come to later. And apart from that, we have every particle we have an antiparticle, and every matter we have the antimatter. So basically, we have the media experimental evidence. We can also separate the particles and particles in the experiment. Now the other question is, okay, we have so many particles, we have so many the bound state, like bound state of one of the bound state is the proton. Proton is a bound state of 3 quarks, and pion is a bound state of 2 quarks. So, but how all the quarks are coming together? What holds all these quarks inside a small size? There should be some force, there should be some pressure from outside. So there are apparently many types of forces in the universe. They're all based on 4 fundamental forces. We know the gravitational force. We know the electromagnetic force. But there are some other weak force and strong force. Strong force. So if I comment on the strong force initially it was suggested when people were thinking about the nuclear structure. People were thinking of, okay, so far we know that gravitational force, because two massive bodies can always attract. Also, we know the electromagnetic force, that's also very well defined from the Maxwell equations. And later, when the nucleus discovered and the proton also discovered, and so many experiments was performed, now people were thinking that how the protons, so many, like suppose in the nucleus of the lead, around how many protons? 92, and in the gold atoms around 70 protons. How all the proton with the same charge, it can be existed in a small size, suppose in a small size of nucleus, because there is a high repulsion from the electromagnetic force. So at that time it was suggested that there should be some other force that should be very stronger than electromagnetic force, that bind together all these proton, so that it can be stable inside the nucleus. So it was suggested Ecole, then at that time it was suggesting that there was some exchanging particle. We will come to that point. So anyway, we have four fundamental forces: gravity, electromagnetic the force, and the strong and the weak force. The strong and weak force only act very short distance. What I mean is short distance. Short distance means, you know, the gravitational force and the electromagnetic force. It is always the range of this force is infinite, right? Although it is, if the two objects, like two charged particles, if it is at this distance, there should be some significant electromagnetic force between these two charged particles. But if I increase the distance, the electromagnetic force between these two charged particles will decrease. But if I increase the distance, it finally decrease very in a small value. But it is always, there is some small or least value of some force. That's also saying in the same case for the gravitational. But for the strong and weak force, it is very short, means after some distance. So strong force only maximum is 1 to 2 Fermi. So beyond that, this force can be valid. This force can act anything. It can't do anything. So that's why it's a four very short distance are responsible for the nuclei together, are responsible for all the protons holding inside the nucleus. Also, you know that electromagnetic force act between the electric charges, and the gravitational force acts between the masses. Okay, so but how the force acting, how this interaction, all this gravitational or electromagnetic force, all this force act other particles. We know it's not like physical support, or it's not like physical interaction. It's not like physical binding. So how they interact? We know that from the magnetism and the gravitation, how the force is acting. So in this case, that there is the between two magnets, the electromagnetic field is interacting between these two. But how, anyway, fundamentally what happens here? So that's the question. A force is not just something that happens to a particles. It is a thing which passes between two particles. Means there is some particle is exchanging between these two. Because of the exchange, there is some bonding, there is some interaction, there is some force experience each other. So it's like that this magnet exchange some particle to this magnet exchange this. So that bonding is developed. That bonding developed into force each other, experience each other. So this is the way two particles, two objects, or any massive bodies, everything in the universe is interacting. So that's why I wrote here the force carrier. We have some fundamental constituents like the leptons and their antineutrinos, their neutrinos, and we have quarks, and we have the force carrier that will be interacting, that will be exchanged between these two, between these quarks, between these leptons. So it is like that. That is an unseen effect. How the force carrier is one good example is that we have the two people standing in the boards, and one person is throwing some baseball to the other person. It's like that they are receiving, they are exchanging force carrier to this person. Then while receiving this force carrier, in this case the ball, he will experience some force, then he will move back. So similarly, all the forces in the universe is because of the exchange of some force carrier particles. So this is, we have the experimentally evident we have this proposal and a different type of particle. Okay. So this is one of the good example how the force carrier is acting in each interaction. So summary of the interaction force is, for the gravitational force, we have the force carrier. The force carrier is graviton. It is not yet discovered. It is not yet observed, but it is it is very well defined in the theory. And we have weak and electromagnetic interaction. So what is weak interaction? Weak interaction, why it is calling weak interaction? So basically weak interaction is involved with the neutrino. In that case, why it is weak, one reason is that it is very short range. As I said before, short range means the interaction or the range of that weak force or the range of that force is very, very small. It's not like the electromagnetic force. It's not like a gravitational force, because in the gravitational electromagnetic force, the range is too large. Okay. So in the weak force, also another thing is, it is the time delay. Like in the neutrino, the beta decay. Beta decay is one of the example of the weak force or weak interaction. In that case, neutrino is involved. All the interaction, all the decays that involves the decay, that involves the neutrino is because of the weak force, means it delays that interaction. Also, it is very short range. That's why it's weak. Why it is weak means that the force carrier is too massive. The force carrier is the larger and massive particles. Because of the force carrier is too massive, it can't go to far. It can't go to at far distance. That's why it's a short range force. Here the force carrier is WZ bosons. We say bosons. And in the electromagnetic force, we know that. What is a force carrier? That is a photon. And in the strong interaction, the force carrier is gluon. So we know the photon, but maybe we understand, we may study it in the earlier classes, at least the name of some bosons. So all the force carrier are bosons, all the force carriers. Here in this case, graviton. In this case, sub WZ bosons. And in this case, photons. You know, the photon is massless. That's why it's a long range. It's an infinite range of force. And gluon also massless, but it is short range because of it's a color charge interaction. So how it is interacting? Gravitation is interacting with all, because all the massive objects can be affected by the gravitational force. What are the weak and electromagnetic force? It will interact with quarks and leptons. Here the electromagnetic is all the charge particles, and the strong interaction only with the quarks and gluons, not other particles. Like strong force will not affect electrons, will not affect neutrinos. Okay. Okay. So far, we have the elementary particle from different experiment. As I suggested before, we have 48 matter and 13 force carriers. Where is that slide? Sorry. I missed one slide. Yes, so far we have, this is the summary of the interaction force. So far we have the elementary particle this is like a periodic table for the fundamental particle, for the elementary particles. So as I said, this is up quark, down quark, charm quark, top quark, strange quarks, bottom quarks. And you can see the mass and this one, the charge of each quarks. Also, as I said, each particle in the universe has its antiparticle. We can see the antiparticle in this structure. So we have the leptons here, electrons, muon, tau, and the corresponding neutrinos, and their antiparticles and their corresponding anti-neutrinos. So far we have 61 particles from all together, and that's a 48 matter and 13 force carriers. So basically, why it is 48 matter? It is saying that only 24 and some below 30. So it is because of the fact that we have a color charge for all the fundamental particle, like quarks and gluons. We have the color charge. So each color charge is different for different quarks and gluons. And here is in the red, we have the force carriers. As I said, for the strong interaction, gluons. For the electromagnetic, it is photon. And for the weak force, it is a Z boson and the W plus and W minus boson. And also we have the famous Higgs boson also. This is the real reason for the mass generation in elementary particle. It gives this Higgs field exchange the mass to the other particle. So far we have 48 matter and 13 force carriers. What it means, matter means, so matter means using these elementary particle, all the matter are built, whether it is stable or unstable, or the matter particle like the protons, neutrons, kaons, pions, all other particles were built using this matter, and these are their corresponding respective force carriers that bound together that binds the quarks and that bind together some leptons. Okay, so the interesting thing is that all these particles most of the particles were suggested by or predicted by in a well-defined theory that we are calling standard model theory. This standard model is very well tested, very well. It was suggesting many particles, and according to this theory, many particles was discovered. So the standard model theory predicted most of the particles. Most of the elementary particles were discovered in high energy accelerator, as I told you before, like in CERN, LHC, SLAC in US, BNLA in US. And the pupils, scientists were working hard to find the study and to understand the fundamental constituents, to understand the nature of the matter. And it is still going on. It will still go forward. So this is just, I will show you how the things are changes from how the sizes and then how the different, how will I say, experimentally verified things going up. From the Wiras, from molecules and atoms, then nucleus, then protons. These were some developments of the different stages of the scientific development, scientific discoveries. And from the nucleus, we reached the proton. From the proton, we are reached here. We are reached means so far the fundamental or elementary particle is quarks and leptons. And yes. As I said, the accelerator is a powerful tool. It's like a microscope. Using microscope, we can amplify the smaller object into a bigger size, right? The similar way, in a similar approach, we say that we can study the structure of the smaller object or a smaller particle using the accelerators, using the same principle that de Broglie, the wavelength principle. So we use particle accelerators to increase the momentum of the probing particle. Probing particle means the incoming particle, thus decreasing its wavelength. So that we can understand. So far, the quark size is around 10 to the power minus 18. 10 to the power minus 18. See. So from the the cell is around micrometer, 10 to the minus 6. So using other equipments, electron microscope, we can see the smaller object like 10 to the minus 8. But the accelerator, using accelerator, high energy accelerator, we can understand the very smaller, like 10 to the power minus 18, up to 18. So far, we can understand the smaller structure of the particles. Okay, let us see how the LHC accelerator is working. See now okay, I will show you here. Oh, sorry. The proton is going into the beam. The proton first accelerated in the beam. Here the proton entered. The proton is ionized from the hydrogen or in any other atoms, like other atoms. We separated the protons and we injected the protons in a beam like this, and we then accelerate. Accelerate means we increase the speed of the momentum of the protons beam, protons particles. See, using this we can increase there are 1,000 bunches of the protons. Now using inject it will rotate here, then it will increase its momentum, then proton will come to here, then again we will rotate the protons beam, the bunch of beams. In each bunch around billions of protons in each bunch, in each group. Then we increase the momentum and energy of the proton so that we, as we said, if you increase energy, the wavelength will be reduced so that it can go, it can interact with the inside particles. Now this is LSC tunnel under the earth, around 27 kilometer, the circumference, around 27 kilometer circumference. We have 4 experiments to understand, to detect, to collect the particle that produced from the collision of the protons. We have 4 experiments, that is CMS, ALICE, ATLAS, and LSCB. See, the particle is coming through this beam. Oh, it's showing something else. So the 2 protons are colliding here, and new particle is producing. It is collected some detector in the experiment. Okay, see, the new particle is produced. How the particle is produced? As I said, it is like from the Einstein-Famous energy, the energy mass equation, E = mc square. If you have a high energy particles, that energy, that relativistic kinetic energy will be converted into the production of new mass, new particles. That's the principle is used here. Okay. So then it is collecting in the detector. Okay. So this is the one of the detector, as we have seen just in the last video. So this is the size of the detector. You can see some human being here. So we have a very, very big size detector to collect all the final state of the particle that is produced in the proton scattering or any other electron scattering. So this much is effort. Like we have to understand this very sophisticated electronics readout, and we have to have some the very precise understanding of each cross section of the particle interaction with the material, so that we can collect all the particle produced in the collision. So this is like a joy. Once this is the real happening in the experiment in the CERN. Once where they started the experiment, they collect the data, they collect the particles in the detector. Then they understand. Okay, when they feel that okay, this is we got real particle. then the people are enjoying like this. So this is still continuous. This is just happened in yesterday. LSCB, I told you in the CERN, in the LSCB we have 4 experiments. One of the experiment is LSCB discovers a new type of Quark. Means so far we have bond state of 2 or 3 quarks. That's a bond state of 2 quarks called mesons, and bond state of 3 quarks called baryons, like protons and neutrons. Now, this was suggesting this exotic, this unstable particle some years back. There is a possibility that for the bond state of 4 quarks, and it was just discovered yesterday at LSC in this LSCB experiment. So the people are still continues their hard work, their search, their understanding to understand the nature of the fundamental particles. So curiosity still continues. Do you want to be part of it? So with this, I end my talk here. Thank you for your attention.
Thank you, Abdullah. Thank you, Abdullah.
Yeah, we can hear, sir.
Okay. Principal sir, please continue.
So it is the time for the interaction. And the students got a wide and very good explanation from Abdulla Abdulsalam. So please. I hope that the students got an international experience, just exposure. So you can just ask, or you can share, or you can have any doubt, or you can add, or something, anything. Just students or teachers or anybody.
Hi, sir. Good afternoon. I'm Jasmine. I'm a former physics faculty of Wiras. In 2012-13, I was there. Sir, my question is, out of curiosity, I'm asking, do you believe like in future the quark will also undergo a splitting?
Yeah, good question.
Thank you, sir.
Yes, I personally, I believe, but until so far, there is no evidence for that, but it is, we have a, how will I say, logically, rationally, we can believe that while we're discovering the nucleus, at that time that the people were thinking that nucleus is something fundamental and elementary, and later the technology advanced and the experiment, new understanding is the people could understand it, people can understand more from other experiment. Now they realize that no, the nucleus is not, then proton, then people were thinking of the proton was the fundamental particle. Now then they evolved understanding that they evolved from the understanding from different experiment that every particle is structured. Every particle is something have some other smaller particle inside. But it is not experimental evidence, but rationally we can say, okay, it could be in future other experiment, and it could give some new light on the structure of the quarks. Yes, I personally believe it should be.
Okay, we should also believe like that. Sir.
Yes. Also, other thing is that one of the force carrier is photons, and the photon, as I said, photon is the boson, one of the elementary. We consider one of the elementary particle, but there are some significant studies were performed on photon that photon has something inside, especially from the mixture of some electrons and positrons. Yes.
So the floor is open for all. So they can invent, right? The remaining things.
Yes, sir.
Inshallah. Okay, carry on.
മലയാളത്തിലും ചോദിക്കാം. Anyone wants?
Yeah, if any students want to ask any question in any language, it's not a problem, I think.
It's not a problem. We want only plans. Okay, sir, please.
Good evening, sir.
Yes.
Just
please.
you can switch on the video before calling. That will be better if you can.
Yes, yes, better.
I'm Fatima PT and I'm second year student. So my question is, we have already heard that the teleportation of different particles, small particles to different countries. So my question is, in future, it is possible for the teleportation of human being or some spaceship?
I can't hear you well. Sorry, Fatima. Can you?
Sir, I have seen in many videos that the teleportation of some smallest particles like proton to some countries. So in future, it is possible that the teleportation of some spaceship or human being, it is possible, because I have seen some videos. That is why.
Fatima, I can't hear you.
Sir, can you hear?
Now it's okay. Better. Yes.
Okay, sir. We have already seen some video that the teleportation of some smallest particles like proton had already teleported to different parts of country. So in future, is it possible for the teleportation of a spaceship or human being?
Yes. Okay.
Because I have seen video, that's why I'm asking.
Sorry.
Because yesterday I have seen some video that in future it is possible for if you're controlling that wormhole. Yeah.
Yeah, it's possible in the sense that so far as I told, to understand the inner structure, the basic or the fundamental constituents, we need very high energy accelerators. So in the future, already declared, at least in the Europe and the Europe agency, the CERN and some from the US also. So far, the energy level is maximum 10 tera electron volt. That is upgraded. That will be upgraded to 100. It means that we can go deep into the very smaller particles of quarks and other smaller object. So it will definitely give the new lights, new understanding for the fundamental particle. Yes.
Okay, sir. Thank you for the information.
Okay, others. And we have enough. Means 6 more minutes are remaining. Our vice chairman and the father of Abdullah is already joined. So he can say some words. Salam, sir, please. Unmute it. Please unmute it. Unmute it. Salam, sir.
Assalamu alaikum.
Salam.
I'm very happy to see you all with my son. Anyhow, it's a nice and very blessed things. I don't know how far effective was the lecture, the series, the seminar. I was only in between few minutes attended this program. Anyhow, I think the students might have got some points. Wish you all, and I wish this program is success. And for Abdullah, especially, very thankful to accept our invitation for our Wiras. I think his former college faculty teacher also with us, Professor Ramachandran. So he can also give some words, I think. May God bless us. Assalamu alaikum warahmatullah.
Both of them shared their experiences. Professor and student, both of them shared. So that will be a great inspiration and motivation for our students also.
Definitely.
Yes, I want to add regarding this. You have a good opportunity, or you have a great high occasion that Professor Ramachandran is with you. Really, I'm not just saying some general words. It's really you have to use him, you have to explore him. He has a good capability in physics and a good knowledge and sincere knowledge. Yes, please explore him, please, all the students.
Inshallah, we will use him very well.
Okay. It will be too much from Abdullah anyway. One thing I want to tell is that initially we were planning to conduct the webinar yesterday, but one day after we have got a new knowledge. It is the Terra Quark. That is a just a newly born thing. So that much novel idea we have got. So one advantage we have got with this postponement is that Abdullah has shared the latest as far as the particle physics is concerned. And many congrats for that, for sharing with us. Many thanks also. And all the other things we can see what we are going to see. We need not explain. Okay.
Okay, my dear students, means you can ask some more questions.
Hello, sir.
Yeah.
Hello, I am Rasmia.
Yes.
Actually, I am not an expert in physics. I am MTech in computer science. But I have a curiosity. Sir?
Yes,
can you hear me?
Yeah, I can hear you, yes.
Sir, how can we isolate protons? Is it bound in the nucleus?
That's a good question, yes. So, in experiment, usually we have different species used to accelerate, to collide the particles.
Okay.
So to collide the particles. So one of the species, there is a proton, as you asked. Other thing is electrons also we are using to interacting this one. Also sometimes ions also used. So your question is how we are isolating the protons from the nucleus. So in the proton-proton interaction, we mostly use hydrogen atoms. So to strip the electron, you just give them some more energy, then it will be ionized. You know okay, you are from the MTech background, so we can say that. So it is well defined that how if you give some specific, in this case of the hydrogen, if you give some 13.6 electron volt, you can separate electron from the hydrogen atom. So what is remaining? If you separate the electron from the hydrogen atom, that's a proton only, right? So in the proton-proton interaction, in the proton-proton scattering, we use just to separate the electron, just strips out the electron using some ionization method. Okay, so this is easy. So but in the case of lead ion, there are some ions also colliding and scattering in this. So in the case of lead ion, that is a little difficult to separate. So the ions means basically the nucleus. All other the electrons we have to strip out. That's some difficult method. Yes.
Okay.
I hope the answer is correct. Yeah.
No, thank you, sir. Thank you.
Okay, please. ഈ അവസരം പിന്നെ കിട്ടില്ലേ? കിട്ടിയ അവസരങ്ങൾ ഉപയോഗപ്പെടുത്തണം പരമാവധി.
Sir,
Yes, please.
ടൈം ട്രാവലിംഗ് പോസിബിൾ ആണെന്ന് പറയുന്നില്ലേ? അപ്പം നമുക്ക് പാസ്റ്റിലേക്ക് പോകണമെങ്കിൽ ഗ്രാൻഡ് ഫാദർ പാരഡോക്സ് അങ്ങനത്തെ എന്തോ തിയറി സോൾവ് ചെയ്യണമെന്ന് പറയും. ആ തിയറി എന്താണ്? അതൊന്ന് പറഞ്ഞുതരോ?
എങ്ങനെ മനസ്സിലായില്ല? ഒന്നുകൂടി എന്താണ്?
ടൈം ട്രാവലിംഗ് പോസിബിൾ ആണെന്ന് പറയുന്നത്. അപ്പം അത് പാസ്റ്റിലേക്കും പോവാ ഫ്യൂച്ചറിലേക്കും പോവാ. പാസ്റ്റിലേക്ക് പോകണമെങ്കിൽ ഗ്രാൻഡ് ഫാദർ പാരഡോക്സ് തിയറി സോൾവ് ചെയ്യണമെന്ന് പറയും. അപ്പൊ ആ തിയറി എന്താ? അതൊന്ന് പറഞ്ഞുതരൂ.
Maybe some expert from Professor Ramachandran can say more about that. But okay, so far that's a paradox again. But the time reversal can happen. That is very in the sense that how the time is defined. If it is in the if it is defined in the space plus time for 3+1 coordinates, then we can say that okay, it is like equal food, we take the space and time. But if it is in the other leg, the time is unidirectional. Unidirectional means we have the 3 space coordinates. Time is always going forward, not backward. So in that sense, that's a Newtonian approach. The other approach is space-time. The space coordinates and the time coordinates, it is considered as an equal part. And recently there is a development in the time reversal and suggesting that it can go in some universe backward. But in that state, it is considered that time is not relative. Time is absolute. There is 2 terms. What is saying that time is relative, absolute in the sense. Relative means basically it is the whatever we are measuring the time, that is changes in different coordinates, in different frame of reference. And time absolute means that is same for all observer in all frame of reference. So recently, maybe 1 month back, there was a suggestion the reversal can happen in some universe other than our universe, but that is also purely theory. Other multi-universe also purely theory because we don't have such evidence. So that I don't know how to solve this paradox. Maybe Professor Ramachandran can say something more.
So please unmute your.
Sorry, I am not that much familiar with the concept, and I think that is something imaginary thing. I think it is not still realized. Some concepts are there, but I think that is still developing, and I don't have much more ideas on that aspect. You can get some ideas. You can directly get it from Google by Googling, and Wikipedia can give you some basic ideas. That's all what I can say about it.
സലാം സാർ എന്തേ പറയുന്നുണ്ടെങ്കിൽ അത് ഒന്ന് അൺമ്യൂട്ട് ചെയ്യണം.
The question, Fatima, is a very interesting question, but this is all depend upon how the Fatima, are you hearing, right?
Yes, sir.
Yeah. What I'm saying that all the time and the space, this is very fundamental concept in the earlier time until today also. There is some difference in the definition of the time and space, even in the science and plus philosophy. So mostly even then that's why there is a huge difference in the concept of time and space in the Newton, according to Newton, according to the Einstein and some other scientists also. So but it's a good concept. You can carry out some your studies, your research in that field. Okay, thank you.
Once if we can retrieve the time, then everything will change, right?
Yeah, that's how you define. That's a fundamental question. How you define the time? So there are different theory, but the theory means so far we agree on that space and time. Okay, at least we know 3 coordinates: x, y, z, and time. And in the Newtonian mechanics, it says that time is always unidirection, means always forward. As you said, when it is active, it is not going back. But if you take time as a space coordinates, time as a same as space, x, y, z, t. If I take like that, we will get a flat universe. We will get a flat everything. There is no particular direction for the time. It's like one coordinate in the space. So in that sense, we can go back.
Yeah, maybe if we talk about philosophically, I think it's possible, because sometimes once after the death, the Almighty Allah means retrieve all the things back. So you can see everything.
That's why I'm saying there is still some gap in the understanding of the space. So be according to the science also, according to the philosophy of science also. So that's why I'm saying to the Fatima, you have if you have interest, then go ahead, carry on that field.
That's a good question and motivating question, Fatima. Keep it up.
Thank you, sir.
So if any others are there? Ramandan sir, if no more questions, we can wind up, right? Sir, please unmute. Unmute, sir.
Sir,
yes.
ഒരു ക്വസ്റ്റ്യനും കൂടി ഉണ്ട്. അത് സർ ഇന്നെടുത്ത ടോപ്പിക് ആയിട്ട് റിലേറ്റഡ് ആണോ എന്ന് എനിക്കറിയില്ല. പക്ഷെ കുറെ നാളായി ചോദിക്കണോന്ന് വിചാരിക്കുന്നു ആരോടെങ്കിലും. ഇത് നല്ല ഓപ്പർച്യൂണിറ്റി ആണെന്ന് ഞാൻ വിചാരിക്കുന്നു. ക്വസ്റ്റ്യൻ ഇതാണ്, ഈ പാരലൽ യൂണിവേഴ്സ് സത്യമാണോ? അത് ഫിസിക്സിൽ അത് പ്രൂവ് ആയിട്ടുണ്ടോ?
Okay, again, I'm not expert, but what I will give you what I know. Okay, parallel universe, multi-universe possible ആണോ? ഇവിടെ വരുന്നത് വെച്ചാല് ഇങ്ങനെ വരുന്ന നമ്മള് യൂണിവേഴ്സ്, യൂണിവേഴ്സിലെല്ലാ സ്റ്റാർസ്, ഗാലക്സി, അതൊക്കെ നമുക്ക് മനസ്സിലായി ഇത് എങ്ങനെ ഉണ്ടാക്കപ്പെട്ടെന്നൊക്കെ. സ്റ്റാർസ്, ഗാലക്സി ഒക്കെ is made up of some atoms, molecules, then protons and quarks. That's okay, we understand. The problem is that when we especially the expansion, especially expansion in universe expansion illo adilana oru problem varune. Rendamade even the Milky Way le nammade pinne even the nammada solar system Milky Way le rotate cheyyunnadum avade oru problem ennu vechale സാധാരണ രീതിയിൽ ഒരു റൊട്ടേഷൻ റേറ്റ് ഉണ്ട്, ഒരു റൊട്ടേഷൻ റേറ്റ്. ആ റേറ്റിനേക്കാൾ അധികമാണ് ഇത് റൊട്ടേറ്റ് ചെയ്യുന്നത്. സാധാരണ അക്കോർഡിംഗ് ടു ദ ലോ, അല്ലെങ്കിൽ അക്കോർഡിംഗ് ടു ദ കെപ്ലേഴ്സ് ലോ മീൻസ് using the gravitational effect of all other galaxies, all other stars surrounding the solar system. So it should be some specific, well-defined, according to law, it will be something well-defined, the rotation rate. But the solar system, some different, they rotate ചെയ്യുന്നത് കുറച്ച് കൂടുതലോ കുറവാണ്, അങ്ങനത്തെ ആണ്. ആൻഡ് ഇത് രണ്ടാമത്തെ തിങ് പിന്നെ എക്സ്പാൻഷൻ ഓഫ് ദി യൂണിവേഴ്സ് പിന്നെ നമുക്കറിയാം അതൊരു ബിഗ് ബാങ് തുടങ്ങിയത് എക്സ്പാൻഡ് ചെയ്തുകൊണ്ടേയിരിക്കുന്നു. എക്സ്പാൻഡ് ചെയ്യുന്നതിന്റെ റേറ്റ്, അതിന്റെ ആ പിന്നെ തോത്, അതും അക്കോർഡിംഗ് ടു ദ അന്നുള്ള എക്സ്പാൻഷന്റെ ഒരു റേറ്റിനേക്കാൾ എത്രയോ മടങ്ങ് അധികമാണ്. അവിടെയാണ് സംഭവം വരുന്നത്. സംതിങ് ഡാർക്ക് മാറ്റർ, ഡാർക്ക് എനർജി, ദാറ്റ് മേ ഇൻഫ്ലുവൻസ് the rotation, the expansion of the universe. Then to explain that dark matter, dark energy, the present theory is not sufficient. Present theory, as I told you, the standard model theory and the available theory is not sufficient. അപ്പോഴാണ് ന്യൂ തിയറി വരുന്നത്. അങ്ങനെയാണ് ന്യൂ തിയറിയിലൊക്കെയാണ് സ്ട്രിംഗ് ഡയമെൻഷൻസ്, സ്ട്രിംഗ് തിയറി, അതുപോലെ തന്നെ എം തിയറി എന്നൊക്കെ 2-3 തിയറി ഉണ്ട്. ആ തിയറിക്ക് പ്രകാരം നമ്മൾ സാധാരണ മാക്സിമം 4 ഡയമെൻഷൻസ് ആണ്, 3 സ്പേസ് ഡയമെൻഷൻസ് 1 ടൈമും. അതിന്റെ സ്ട്രിംഗ് തിയറിന്റെ പ്രകാരം 10 ഡയമെൻഷൻസ് ആണ്. അപ്പൊ 10 ഡയമെൻഷൻസിന്റെ ഒരു പോസിബിലിറ്റി എന്താണെന്ന് വെച്ചാൽ അത് മൾട്ടി യൂണിവേഴ്സ് പോസിബിൾ എന്നാണ്. അപ്പൊ സ്ട്രിംഗ് തിയറിക്കാണ് മൾട്ടി യൂണിവേഴ്സിന്റെ സാധ്യതകൾ പറയുന്നത്. ബട്ട് so far no evidence. Without evidence we can't say whether it is exists or not. We don't know. അത്രേ. പക്ഷേ തിയറി പിന്നെ how will I say, ഒരു പിന്നെ പവർഫുൾ ആർഗ്യുമെന്റ് ആണ്. പക്ഷെ വിത്തൗട്ട് എവിഡൻസ് നമുക്കൊന്നും പറയാൻ കഴിയില്ല. അതാണ് അതിൽ പറയാനുള്ളത്. പക്ഷെ ഐ എം നോട്ട് എക്സ്പെർട്ട്. യു ക്യാൻ സെർച്ച് മോർ.
Okay, sir.
No more questions, I think.
So if it is like that, so we can wind up the session. And thank you, Abdullah. Thank you for coming here and interacting with our students. And I invite Muhammad Ismail, Association Secretary, Department Physics, to express vote of thanks. Ismail, are you there?
Yes, sir.
Yeah.
Yes, sir. Good evening to everyone. First of all, I thank the Almighty for giving me an opportunity to attend this webinar. It was an excellent seminar, and Abdullah Abdulsalam sir have given us a clear-cut idea regarding the fundamental particles and fundamental force. Thank you, sir. I expect more and more seminars from him on various topics in the future. I also thank our principal, Muhammad Iqbal sir, academic director, Muhammad Sajid PK, secretary, Mr. Farooq Usman, and SLP Salam sir, who always strive to give us a good future. I also thank our dear teachers, Ramendran sir, Jasra miss, Safina miss, and other teachers who are present here for encouraging us with lots of webinars. And thank you for everyone for joining this meeting. Thank you, sir.
Okay. Thank you.
Thanks, sir. Thank you.
Okay.
Thank you, Abdullah.
So I will leave. Okay.
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 So we shall leave. Okay.
Okay, next നമ്മുടെ സ്റ്റുഡൻസിന്റെ ഒരു വെബിനാർ ആവാം അല്ലേ നമുക്ക്?
If anybody is ready, we can conduct the webinar.
Okay, sir. Thank you.
Okay. So I am leaving.